think I'm in the right one. Click on the right thing. I did. Okay. Zoomy, zoomy, zoomy. I can do this. Hi, Brooke. Cool. How about our course log? Did I do that? Course log. Yay, okay. We got a full Zoom room today. Howdy, Zoom. We're still waiting on, how many do I have here? 5. I've got 4 here. That's 9. We're also waiting because Lexi was going to stop by today. The other Lexi, the SI Lexi, was planning on stopping by today just to say hello and like answer any questions you might have about SI. So I'm gonna wait for her. Nobody took me up on my, so I'm a little sad. Nobody took me up on the is a hot dog a sandwich in the chat on Zoom the other day. Is a hot dog a sandwich? It's its own separate category. Hmm? Yeah.
Yeah, so there's a hot dog council or something like that that like officially said hot dog is something.
There's a hot dog council?
It's something like that.
I saw. So I think that a hot dog is actually a taco. I think that's the proper isomorphism there, right? Because of the number of like sides that are encased of the object that you are eating. Yeah, if you split your hot dog bun in half, then I think you're in sandwich category. But if the hot dog bun is conjoined, you're in taco category.
I don't need buns.
Yeah.
National Hot Dog and Sausage Council
announces the official policy on hot dog.
Oh my gosh, I am going to like cause some waves if I make that known. There's a whole group of mathematicians on Twitter called the Hoagie Homies who have intense debates about what constitutes a sandwich or not. And they told me, they're like, I do this exercise with my students all the time, and they get so wrapped up in the debate about like, is a hot dog a sandwich or is cereal a soup? And he's like, it's the best like opener ever. And every single one of my classes, I was like, is a hot dog a sandwich? And they all just stared at me and did nothing. I'm like, this did not work for me, you liars. Yeah, I mean, I feel like I ought to defer to the hot dog authorities, of which I am not. Yeah. Yeah, that's all good. Yeah, absolutely. You're welcome to go either place. We have SI because it just offers more opportunities for you, and it's not meant to be like a substitution for me. It's meant to be like another place to go, right? So you can ask Lexi, you can ask me, you can ask both of us, you can ask neither of us, whatever is your comfort level. And it's a little bit weird too, like what Lexi also has to navigate is that there's a brand new head of tutoring right now, and like they are making changes to the SI program from the way it's been in the past. And so she's also got to try to navigate like the experience that she had with her SI is not necessarily the experience she's being told that she is meant to do. So I think she's still navigating like, what am I meant to do in this job? And we'll figure it out. Like all things, the ball will get rolling on the semester and we'll figure it out. Other thing I will say for you now, because Lexi will pop in when Lexi will pop in, we'll get started on the day so that we have time to get through everything we need to get through. But the one thing I did want to mention to you is that right now, our first exam is scheduled for September 30th, which was 2 weeks from Wednesday. So it comes up really fast because you're not like, it almost feels like the first day we were in person was like the first day of school, but it really wasn't. We have those 2 weeks of time ahead of time. So be prepared that right now your first exam is scheduled on September 30th. I have your exams roughly scheduled at the end of each month so that we can have an exam at the end of September, October, and November. And then you have final projects for that December timeframe. There's not an exam during your final exam period. So just wanted to put that on your radar. Before either Lexi gets here or we all start for today, like, do you have questions, other questions or comments or things like to talk about? You're all right? Okay, I'll do one more killer of time before we start talking about what is and is not a group. The killer of time is, I feel very badly for you all because you have so many different classes and every class is finding its own unique solution to 2020. And that means like some things are on YouTube and some things are in Schoology and some things are remote and some things are synchronous remote and some things are asynchronous remote and sometimes you're in person and then sometimes you just have to wait for your professor to tell you what you're doing that day. And I think it just is super overwhelming. Like you have a different system for every single class. Sometimes you don't even know what the system is. So I'm trying to be as organized as possible on Schoology for you. But if there's something missing or that's not like making sense, let me know so that I can like try to be as clear as possible there. And then I'm going to try also to remind you in class of like what needs to be done for the next class, just so that like the more reminders we have, the less likely it is that something is going to happen where you're like, oh crap, I just like totally didn't even know that was a thing. So I'm going to try to remind you. For Monday, there's one video in a YouTube playlist that I'd like you to watch. So it's one video, it's less than 10 minutes. Watch that before Monday, because on Monday, I think we'll be past these examples and we'll be moving on. And we're gonna focus on writing a proof all together in class on Monday. And it's gonna be based on the proof that I do in this video for you. So it's really necessary to watch that ahead of time. And then generally when I assign you videos to watch outside of class, I'll just have a brief quiz of some nature to like keep you accountable for doing that thing. If you were to not watch the videos and then come to class and then have no idea what you're doing, and then I have to also explain what was done in the video, we lose that collaborative time to be working on the hard thing, which is the proof that we like want to get through. So for Monday, there's one YouTube video to watch, and there is a Google form quiz that's like 3 questions maybe after it. Just brief thing like, did you watch it? That's what we have for Monday. That's all we have for Monday. One video, one quiz. Good so far?
Where's that video?
Yeah, I think I posted the to-do. That's the thing I don't know. Where does the to-do list for Monday go?
It's in the plan 14 that says to do for Monday.
Yes, yeah. I can't tell where the Monday should go. And I think, like, does it go at the end of the last week or into the new one? Honestly, I'll probably put it in both spots just because, like, I'd rather have it in more spots than fewer. Other questions before we get going? All good?
I have a question about the homework.
Sure.
If we worked with someone else, should we both submit a copy of the homework?
Yes, that is a good question. Okay. If you worked with somebody on the homework for the whole homework assignment and you're turning in a joint homework assignment with both names, which I'm fine with, you can turn it in with just one person as long as it says both people's names on it, right? So because otherwise, if you don't turn it in and you worked with somebody else, but on that paper, it doesn't say your name, to me, it looks like you didn't do your homework. So just make sure both names are on it and then one copy is fine. If you work with other people on because I know that collaboration is like kind of a messy gray area of like what is working on. What I really generally appreciate is just like more information. So let's say you didn't do your whole assignment with somebody else, but you were like hanging out after the SI session and then you like all solved whatever problem together. And like you did problems 1 through 4 on your own, but the 5th problem you did with like a group of people. If you just make a note of that, then that's useful to me. Just like I didn't work on this whole assignment with everybody, but I was like, we solved this problem together is just useful. The reason that that's useful is that especially if you're talking about a problem in a room and you're all chatting about it, and then you leave the room and the next day you go and write up the homework assignment, it will not look the same as somebody else's. Like it will look similar. I can tell that you have similar ideas, but it will never seem word for word because there's no way, it is like statistically impossible that you wrote it up a day later in a separate room and you chose exactly the same words and cadence as somebody else. You might use the same variable names, you might have the same ideas, but it's not gonna look identical. If you worked with somebody else and you wrote the proof at a table next to each other or over Zoom together or whatever it might be, it can start to look identical. And if you don't tell me that you worked with somebody else, that looks like plagiarism to me because I see 2 people, no record of the fact that they worked together and their answers are word for word. That looks like plagiarism. It could be plagiarism. I assume actually that it's not because I trust you all and know that you're collaborating and trying to learn. Like you're good people and I generally trust you, right? But because it could be plagiarism and I don't have any indication, like I have no knowledge that you all work together, I will have to talk to you about it and be like, do one or the other, right? Like either write that you work with somebody or write it up in a separate room so it doesn't look this close. But I just need the information of like what sources you were consulting and who you were working with.
Okay, I do
Yeah.
have a question
Sure.
that you just reminded me of the homework thing. Is there a way for us to submit a single PDF with scanned documents from a notebook and a Microsoft Word document? Like for the triangle drawing, it was easier to do on here. but
Yeah.
then writing the proofs and color coding is easier to do on Microsoft.
Mhm.
Is there a way to combine the two into one document?
I would think so. Yeah. What do you think, Calvin?
What I do is I just have I take like screenshots of each page.
Yeah,
Mhm.
just take a picture of this, send it to my email, and then screenshot it,
Yeah.
put it into the doc.
Like the PDF software, I use like paid for subscription.
Mhm. I have found, the other thing that I've found is when I have two PDFs and I want to merge them, I have found that if I just Google like PDF merge, that you can often find software that'll just ask you to upload the two PDFs and then it'll output one PDF for you.
Right orders, you know, problems, because that's what I was like, okay, 3,
Yeah.
4, and 6 of this homework, like after 2 and 5.
Mhm. It's generally nice if they're in order, but it's not necessary. Like I'm a big kid. As long as they're numbered, I can figure it out. Like I'm not going to give you on 0 on both problems because 2 didn't come before 3.
I wrote you a note on mine because some of the ink like bled onto the back and then one of the problems was kind of hard to read. So that's why I was asking that.
That's all right. I like when I get notes on the homework. It's refreshing. We'll wake up. Other questions or comments? Are you doing okay?
I'll take this.
Okay. Well, yeah, I mean, I feel like that always comes with the, are you doing okay given that you're in abstract algebra during the year 2020? Anywho, let's see if we can get through these. I'd really like to get through all these examples of groups today. We have a good number of people joining us through Zoom today. And so what I'm going to try to do, I have this up for you. This is the worksheet that we've been working with. I have it up on Schoology. I know given the angle and where I'm standing, it might be a little hard for you to see, Erin, but you've got your computer, so you're good? Okay, awesome. What I'm going to do for us today is I'm going to try to get all these answers in the course log because we're going to have to like introduce notation and stuff for the things that are groups. And I want everyone on Zoom to be able to see it really well. And it's kind of hard to write on the board with the Zoomers seeing. So I'm going to model how we put all this stuff in the course log and then everyone can see it a lot better. Cool? Okay, we had done, so I'm looking at this, we had done 1 through 5. 1 through 5 we did all together, so we're feeling good about those. We had jumped in and talked about 11, 12, and 13 because those were relevant to your homework, and so I wanted to make sure you got there right away. There were some other groups we didn't talk about on your homework and explicitly do examples with, but those were groups like real numbers and complex numbers under multiplication, and I'm assuming that you feel decent there. The complex numbers might be a stretch. It might have been a while since like you were working with the complex numbers. And so I don't, depending on the atmosphere of the class, I sometimes either take a lot of complex numbers or not a lot of complex numbers. What's your comfort level with complex numbers? Pseudo, right? Normally, if I have a lot of engineers in the class, people who are pre-engineering, they're like, complex numbers, those are the best, let's do this, please. And otherwise, people are like, well, I haven't done it since I was taking the square root of -1 in high school, but yeah, I know what I is. You tend to fall into 2 categories. I'm not sure how many engineers I have in here, but I don't think that many. Okay, so don't bash your brains over it. There are other groups, right? We'll get there. Anyway, we were looking at the next chunk of examples that I think we're looking at. I think it makes sense to go back to like the top and start looking at 6 now, because I think we'll get through the list no matter what. So by my notes, it was Ronnie and Erin and Marquel who had 6 through 9. Is that right? Okay, I've got Marquel on Zoom and I've got Erin over here. So I don't know how we're gonna have the pair of you collaborate on who's gonna present on 6 through 9. So do you just wanna take turns? Okay, let's have Aaron go first and tell us about number 6. Do you think, did your collection of peers think that number 6 was a mathematical group? You said yes, and you're exactly right. The group of 2 by 2 matrices with real entries under addition, that is a group. If you add 2 by 2 matrices, how do you add matrices? Component-wise, right? So if you have matrices of the same dimension, what's ever in like the first quadrant, you just add those together. What's in the little second quadrant, you add those together. Adding 2 real numbers gives you a real number, so your new thing will be a 2 by 2 matrix. The entries will be real numbers. It's got closure. It's got associativity because I said so. What's the identity in this group? Instead of a single 0, it's just like zeros everywhere. The 0 matrix is going to be your identity. And how about inverses? Negatives everywhere, right? If everything's done component-wise, it's kind of like you just have R's in like 4 little spots. And you're like, yeah, well, the real numbers are a group under addition. So this thing is a group under addition. And everything just sort of scales up like it did for the real numbers under addition. So you're exactly correct. So let's head on over here. I'm going to leave 5 blank because why not? Oh, come on. Don't be silly. Things. Okay, 6. Okay. The answer here is yes. So we'll type that in. And now what I want to do is add the notation. I'm going to scroll up a little bit so that you can see better people who are in the class. Bye-bye, Zoomers, for a minute. Scroll up. Okay. Come back, Zoomers. I feel like I'm saying boomers, and then it feels like it's an insult, but it's not. No, now I can't see you. Oh, there's questions in the chat, and I was ignoring them. Oh, okay. Markall handled it. He handled the fact that I wasn't looking at the chat. Thank you, Markall. All right, I lost you. I can't see you anymore, but you all had your screens off anyway, so we're all good. Okay, yes, this is a group, and I want to mention the notation for you. So all that was really important was that the real numbers were a group under addition here, right? I can extend this example in numerous ways. I could have used the integers or the rational numbers or the complex numbers. Like I could have said, how about 2 by 2 matrices where all the entries are integers under addition? And it would have worked because the integers are also a group under addition. So anything that was a group under addition could be that set, and we'd be looking at 2 by 2 matrices and it would still be a group. And similarly, the 2 by 2-ness wasn't even important. What was important was that I generally had like matrices of the same size. So there's a notation that we use for this, and I think that this works for, humbug. There's a notation that works for this, which I think is the same as Galleon. Galleon does one of 2 things. So let me write the notation 2 ways, and one of those ways will be the way that Galleon does it. Right? So he might write M sub n of a set S, or M of ns. He writes one of those 2 things is the way we denote this set, this group, where S is a group under addition. Now, that looks like garbage to you. What am I doing? Here's what I'm doing. For me, I like to type in TeX. And in TeX, when you want to make an equation, you start the equation with $2 signs and you end the equation with $2 signs. So what I'm doing is writing the code that I would write in TeX for how I would want to display this thing. And then I have an add-on for our document, which is auto LaTeX equations. And it puts a little pop-up over here. And all I do is hit render equations, and it takes a minute to think, and it's going to take the TeX and it's going to convert it to a picture. And so it's going to let me TeX inside this document. So I'm going to model that for you. I know you're not all learning TeX, but it makes it for me easier than equation editor. So now it rendered those equations. That's the way it would look in your textbook. I'm not sure if Gallian puts the n right here in a parenthesis or if he puts the n in the subscript. I think I tend to use the subscript. I think Gallian might use the parenthesis when he talks about this group. But if he writes down like, let G equal M sub n of S, what he means is let G be the group of n by n matrices, the M is for matrices, whose entries lie in the set S, and you are to assume at that point that the operation is addition, because they'll have a different notation when we're working under multiplication. So part of the struggle, at some point I'll quiz you on it once we have all of our groups, part of the struggle in groups is getting used to all this brand new notation, because at some point we stop telling you what the group operation is. We just throw a set at you and we're like, this is your group. And it's your job to know in your head what operation that is, right? I will try to remind you of what the operation is, especially a lot in the beginning, but as time goes on, it gets harder, right? Okay, I'm very troubled by the fact that I can't see anyone anymore. I think I have to just like maximize or something, but where did you all go? Yeah, that's the one. That's where I gotta go. I wanted to get this little bar up here. It makes me feel better because if someone were like trying to jump in and like wave at me like, stop, Sarah, I could see it. Anyway, cool. So the answer for 6 was yes. Now let's go back. Let's ask Marquel. Let's go back to the worksheet. How about 7? The set of 2 by 2 matrices with real entries under multiplication. What did you think, Marquel?
Our group said no because if the determinant is 0, which it can be in number 7, then it would fail property 3 and then it can't have an inverse.
Ah, exactly. I don't know how well you can hear Marquel, so I will repeat. They said no for number 7. And what was the problem? If I take a 2 by 2 matrix and I multiply it by a 2 by 2 matrix, I will in fact get a 2 by 2 matrix out. And there's a little formula for how we multiply matrices, which I could write down, but you'll all also know if I do this gesture. This is the way we multiply matrices, right? And I can get away with that because you've taken linear algebra and Aaron Trotwine taught you something, didn't he? I make fun of him and I pretend he never taught you anything in linear algebra. He's okay with it. It's all right. So I can do this and I know you know how to multiply matrices. And in that rule, all that really matters is that when you multiply real numbers and add them, you still get real numbers, which you do. So the closure is not a problem here. Associativity is not a problem here. We have closure under multiplication. We have associativity under multiplication. Do we have an identity under multiplication? Yeah, I see ones, right? Ones across the main diagonal. I'm sorry, I'm mirrored for people on Zoom. So let me see. I do it that way? Ones for people on Zoom. Got to be backwards. Ones across the diagonal, the main diagonal, will give you an identity matrix for multiplication. So you have an identity. But as Marquel's group was saying, we don't actually work as a group because this set in number 7 fails for inverses. There's a formula for finding the inverse of a 2 by 2 matrix. And you have to do something, right? The A and the D get switched and the B and the C get minus signs. And then you need to multiply every entry of the matrix by 1 over the determinant of the matrix. If the determinant of your matrix is 0, you're trying to divide by 0, and thou shalt not divide by 0. So you fail the inverse property in this set if you are a matrix of determinant 0. And then we get to number 8. So let's say that Aaron and Marquel do this simultaneously here. Oh, there's a question in the chat. What's the question? Wait, can you please write that out? Yes. So let's go back to our document and let's write that out. 7. For 7, I'm going to write no. This set fails to have inverses. In the case, a matrix has determinant 0. However, when you look at 8, the set of 2 by 2 matrices with real entries and non-zero determinant under multiplication, you're fixing the problem, right? You're saying any matrix that has a determinant of 0, I'm just going to throw you out. Just like when we were working in the real numbers or rational numbers or whatever, 0 was not invertible and there was nothing we could do to fix it. So we threw it out and we said everything that's left over will have an inverse and will be good. We just do the same thing with matrices. Everything which doesn't have an inverse, I can't solve that problem. I'll just throw you away. And then we already discussed the other 3 properties hold. And so this one does form a group, 8 does. And I will write that along with the formula for taking inverses. That's the wrong one. I will write this along with the notation for this group and the formula for taking inverses so that that's written out for the people in Zoom. The formula for finding inverses. Yes, okay, good. We're on the same page, excellent. Okay, so the answer for number 8 is yes. Let's talk about this one too, because the notation for the group is a little bit strange. We used real numbers. In fact, any set that happens to be a multiplicative group will do. So I could put complex numbers there. I could put rational numbers there. I cannot put the integers, right? Think about this formula again. So let me write the formula for taking inverses of a 2 by 2 matrix is, all right, and now let's see how well this does. This is bad tech, so I'm gonna tech it so it looks pretty. If you're just learning tech, this would be complicated tech. Matrices are a pain in the butt in tech is the point. A, ampersand B, new line C, D. A 2 by 2 matrix is this, and then we negate the B and the C, and we switch the A and the D. And then let's render that equation and hope that it comes out pretty. So I'm getting that formula put in there. Aha! There we go. AD minus BC, and then I have a parenthesis there. So lovely. I will make that prettier in a moment and make that more readable, but I don't want to waste your time with me typing tech up here that is not readable. What we need now is we need the notation for this. I think I asked you, what if I put the integers there? How about the 2 by 2 matrices with entries that are in the integers, right? The answer for that is no, because if I had a matrix with determinant 2, I then need to take 1/2 times each entry in that matrix, and that's probably going to take some integers and turn them into fractions, and then I'm going to fail to have closure, because I start with entries that are all in the integers, and then when I'm searching for inverses, if the inverse matrix has entries that are fractions, I've lost my closure, I've jumped outside my set. So I need these matrices have the form. I probably don't, yeah, I do need that. Sub n of the set S or GL, no. Like this. In tech, when you're in equation mode, have you ever noticed like the cheat way, if you're using Google Docs and you need to put a variable in there, you just italicize, don't you? You're like italics X instead of X, and then it looks like a variable. If you're in Google Docs and you're cheating and you want it to look mathy, or do you not, maybe you don't bother, right? But normally when you look at, which is fine, we're learning, right? When you read a math textbook, variables are italicized. If you don't want something italicized, which I don't to match the notation, you have to say text normal. All commands in tech begin with a backslash. If I want a fraction, backslash frac, right? Backslash is that keyword, like I'm going to put a keyword into this computing program right now. So this is the notation that we use where S is a multiplicative group, multiplicative group. And n, see, I'll just cheat there, is the dimension of the matrix. And by dimension, I mean I'm going to have square matrices. I have square matrices so that multiplication works and preserves the dimensions of the matrix. Why on earth is it GL? Ugh. It stands for general linear. That's the G. Do you remember that 2x2 matrices sometimes give you linear transformations of the plane? That's where the word linear is coming from. So general linear group of dimension n with entries in the set S. It's a weird notation, so it takes some getting used to. How you doing? Doing okay so far? Okay, let's get back to our worksheet then. Aaron and Marquel, your work is almost done for the day in answering questions. 9 was a little bit different. You got 6, 7, and 8 because they were all sort of related to each other and they were in matrices. But I had to get 9 there for you. What if I have a regular n-gon? Maybe like an equilateral triangle or a square. And I'm looking at all motions of that n-gon that preserve it. So if I pick up the triangle and I turn it and then I put it back, and it still looks like the original triangle, but maybe the vertices are labeled. Is this sounding familiar to you? What did you think, Aaron and Marquel? Was that a group? Yeah. And your operation is just like combine them, right? Do this one first and then do the next one. You're exactly right. That does form a group. I think the videos on YouTube were titled this, but I didn't say it a lot in class, that there's a name for those groups. Those groups are called dihedral groups. So I think that's what the videos were labeled, but I don't remember if I've been saying that word or not. Okay, let's think a little bit more about this group. I'll write the notation down in the Google Doc in a minute for these dihedral groups. This at least has a nice notation, except that again, I forget, Gallian and I are sometimes different, but I think I know what he does, and I won't introduce you to even both notations. I'll just do what Gallian does. I will give him this one. Don't always hate Gallian. Anyway, D sub n. If I'm looking at the motions of a triangle has 3 sides, so Gallian would call that group D3. D for dihedral and 3 for the number of sides on the n-gon. So that's the notation that we're going to use. But here's a question. I want us to go a little bit further because we know a little bit more about these dihedral groups. They're an important class of groups. How many motions are there? How many, when we were doing the square, which was the first example that we did in the videos, how many motions of the square did we end up with? Do you remember? 8, awesome. Okay, on your homework that you just did, you did the triangle. How many did you end up with? 6. So if I give you a regular n-gon, how many would you guess there are? 2 times n. Why? That's correct. And that makes sense. Why is that the answer? You have this little n-gon. What do you do with it first? You spin it and you get n of those, right? Don't spin, spin once, spin twice, spin 3 times, and then you're like back at the beginning when you reach n, right? And then what do you do with it? You flip it somehow, and then what do? Spin it again. My hand doesn't work quite that way. Like, you spin the thing, you flip it, and then you spin it again, and that's everything. And we have different ways of describing those motions more concisely, but those are all the things you can get. Spinning it, flipping it, spinning it. 2n, right? So let's head on over to our document here and say, yes, this is the dihedral group D sub n of order 2n. Now, I just said order. Is that a word you remember? You may have heard it. I don't think I've used it here in this class, but you may have heard it in discrete structures. Sometimes the size of a set or a cardinality of a set is called the order of that set. I don't know if people, it's not like a super common thing, but it's a thing sometimes people say. So you may have heard it in discrete, you may have never heard it before. I use that word frequently inside of abstract algebra to talk about how big a set is, right? And then how do we, what's the notation of order 2n? And then I'll write it this way in tech, the size of the set. That's what the order means. You write the absolute value signs around a set to talk about how big that set is. So when I see absolute value of like big group G, I read that out loud as the order of the group G. And it means the size of that set. Cool, okay. How do you feel about that one? Good? Yeah. And I think those are fun ones to play around with. I like it because they're very visual. Somebody asked me about like the technology that they can have on exams, and I was like, your calculator won't help you. But I've definitely had people ask me in the past, can I bring in little models of n-gons? Can I use those on the exam? Can I have like a regular triangle and a square and a pentagon and whatever, and can I like have it labeled, and can I use that as I'm doing my exam? Yes, yes you can, because that's a good visual and that's helpful to you. So you cannot, maybe I don't give you a TI-84 calculator, but I will give you a little polygon to play with if you need. Okay, that's fair. Awesome, okay. Number 10 is one that I get to do, because number 10 is one that I did in the videos. I did this exact example. I said, what if I have this collection of bijective functions on just like the numbers 1, 2, 3? Really, it could just be bijective functions on 3 objects, right? Any 3 objects. But mathematicians are boring and they like just attribute numbers to them because why not, right? I shouldn't say mathematicians are boring. I should say a lot of times it just simplifies things to have a common set. We did this one in the video, so we know that the answer for number 10 is yes for this particular set. What I want to do is show you that notation. I want to do the same thing we did for number 9, but do it for number 10. In the video, I said, okay, I have these 3 numbers, and I have all possible functions that are bijective from the set 1, 2, 3 to the set 1, 2, 3. How many such functions exist? So I think like function in abstract algebra is like, here's a blob of stuff and here's a blob of stuff and I'm going to draw arrows between them. It's not like, here's a beautiful Cartesian plane and the equation y is equal to x squared. I'm like, that's not a function, that's garbage. I want a blob and I want arrows. Because again, this is your life now. We're in weird land. Those are your functions. Okay. Here's the number 1. How many choices do I have for where 1 is going to go? 1, 2, 3, 1, 2, 3. I'm sorry, I'm backwards for people on Zoom. 3 choices, here or here or here. Don't know which, but that's my number of choices for 1. So I make a choice, whatever it might be. I move on to number 2. How many choices do I have for where 2 can go? 2 choices, right? It seems like maybe I have 3, but I chose 1 to go somewhere. And because I'm bijective, I can't go to wherever 1 just went. I have to go somewhere new. So there's 2 choices for where 2 could go. And then how many choices, once I make that choice, there's only 1 choice left, right, for where the 3 is going to go. So my total number of choices is 3 times 2 times 1. There are 6 possible functions that are bijections on the set 1, 2, 3. Good. Now you live in abstract land. Now I have n of them. How many? Is n factorial. This set is called S sub n, the symmetric group, on n letters. I don't know why they say letters when they're numbers, but they do. They'll be like, this is the symmetric group on n letters, and by letters they mean numbers, and I don't know why. because they just want to make your life difficult, I guess. It has order and factorial. Your operation is function composition. You're just doing one thing and then doing the next thing. So this is a group called the symmetric group. Because it's the symmetric group, the notation for it is S sub n, where n is the number of things that you're shuffling. I kind of feel like if you can't remember symmetric group, just think like shuffling group on n things. And then the S makes more sense because that's what you're doing, you're shuffling them, right? This group is a hard group. This group is interesting, but kind of difficult because the operation is function composition. We don't like that, that's kind of hard. We'll probably spend at least a week just going through examples of symmetric groups at some point. At least a week talking about symmetric groups and only symmetric groups. So if you're like, yeah, I kind of get that that's a group, but I don't like it, that's a totally reasonable place to be right now. I'm talking a lot. How are you doing? Are you doing all right so far? I want to go through these things because I want you to have answers and notations so you're prepared to like read and move forward. But I don't want to go so fast so that like nothing makes sense, right? That's a useless place to be. So if ever we need to stop or do an example or take a breather, just let me know. Okay so far? Thumbs up? Zoomers, thumbs up? If you're okay so far? That's not where my camera is. It is unreasonably difficult to mirror your body. Like, have you ever tried, like, have you tried to do like an exercise class where you say right, like where you're leading it and you have to do things backwards but say the wrong thing for right and left? It's like unreasonably difficult. Anywho, we're good. I can do it. I can manage. Hey, 11, 12, 13, we already did. That's nice. So inside my little document, oh, I'm not in there. I'll just be like, hey, did this, did this, did this. And then we're on to 14. And let me look at my notes. Who was on 14? Kyle and Sean had 14 through 16. Awesome. Okay. Set of 2x2 matrices with entries in Z mod 2Z with determinant 1 under multiplication mod 2. That's a big long thing. What did you think? You said yes, it is a group. In fact, you are correct. It is a group. How did you handle this problem? Because I think I remember you handling it and you handled it well, right?
We had to think of all the matrices, because you only had matrix 0 and 1.
Mm-hmm.
2 by 2 matrices, and you have to have determinant 1. So we just we only have 2 matrices with determinant 1 with those entries. It became 0. So then we tested, you can have this is close to this, we know it's a close set. Your identity is 0 matrices, because it's and then you have an inverse, because it's just 0.
Mm-hmm. So what did your identity look like?
It's I don't know how.
Right. No, you're doing the right thing. Kyle's doing this, and I'm going to mirror it in here. He's doing this. He's like, it's this one. And that is the right thing. And the point that I wanted to stress with you for doing that is that it's the same identity that it was even when we were in a way more comfortable place, right? That's the identity you need. One is always going to exist in your Z mod NZs. And so you're going to need that same matrix even if you're working with a weirder set. 1's across the diagonal, 0's everywhere else. That's still your identity like it always has been. So there's like comfort in that, right? Associativity is cool. You just listed them out. This set was so specific that the way to handle it was to like list things out and be like, I listed them all and I combined them and it worked, right? That is what I would do for small examples like this. This example is a weird example, but I wanted to give it to you because it is an example that comes up sometimes. Here's another thing that I will do. It's a place I get to make, I have to do it because I make fun of Aaron Trautwein. There are facts about determinants that I'm not sure that he swears that he teaches you, but people often don't know off the top of their heads. If I have 2 matrices, A and B, and I know the determinant of A and I know the determinant of B, and I multiply those two matrices together, what is the determinant of the product of those matrices? The product of the determinants. Aaron Trautwein gets a prize today. The other thing I've learned from teaching abstract algebra is that everybody loves Aaron Trautwein, which is a thing I already knew. But generally, if I ever have to be gone, he's who comes here. And so when I tell people, oh, I'm not going to be here, Aaron's like, somebody's going to come sub for me the next day. And then I tell people it's Aaron, they all go, yay! So this is just what I need to do. I just need to threaten Aaron Trautwein repeatedly. And then you'll be like, I know it, I know the answer. You're right. When you take the product of two matrices, the determinant of the product of the matrices is the product of the determinants of the original matrices. It's a thing that they supposedly teach in linear algebra, which I guess they do, because Kelvin knew the answer, right? Which Aaron Trautwein does teach in linear algebra. So, in particular, if I have two matrices with determinant 1, and I multiply them together, their product will have determinant 1, because 1 times 1 is 1, right? Their inverse will have determinant 1, because the determinant of one thing, the determinant of the identity matrix is 1, the determinant of the given matrix is 1, 1 times x equals 1. The only solution for what x can be is 1. So more specifically, even if I get rid of the Z mod 2Z's, with the Z mod 2Z's, you could just check. You could just check that it always worked. This property will always hold. The set of matrices that have determinant 1 is a special set of matrices because it will be closed because of this fact. And it doesn't matter what set you're working in, Z mod NZ, Z, Q, R, C, whatever set, doesn't matter. Determinant 1 matrices, their product has determinant 1. That's just a thing. And so we can generalize this example as well. The answer for this one is yes, but when we look at, this is called the special linear group. It's special because the determinant is special. It's a determinant of 1, right? This is called the special linear group, and we write it this way: SL n of s, or text normal. Oh, it should be text normal, not tech normal. SL and S, where S is a multiplicative group, and the determinants of the matrices are all 1. So anytime you have a multiplicative group of matrices, so non-zero determinant, if you look at the subset of them that have determinant 1, those will form a group, and that group is called the special linear group. It's the linear group, but with a special property, which is that your determinant is 1. So that one is ugly. Hey, oh, I did $1 sign instead of $2 signs. That's why it's mad at me. And I did that repeatedly. In actual tech, you can use $1 sign or $2 signs. So I'm going to forget dollar signs a lot at this point. Anywho, that's what it would look like. Notationally, that is what that group looks like. And we did Z mod 2Z for our set S. I could do Z mod PZ for any prime. I could do rationals. I could do real numbers. I could do complex numbers. I couldn't do Z because Z fails to be a group under multiplication. So it gets a little messy there, but otherwise we're good. Actually, I lied. I can do Z. I can't do GLNZ. That's not a thing, but I can do SLNZ. Mind blown. Why? Hint, 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 hint. Hint, hint. This is the determinant, right? The problem I was having with GLN was that, oh, if I have this matrix and it has determinant 2, Then to find its inverse, I need to look at 1/2 times some sort of matrix, and that'll ruin the integerness of my matrix. If my determinant, AD minus BC, is 1, this term right here is a 1. And so this whole fractional part goes away. And the inverse of the matrix is just to switch the entries and negate them. That's a perfectly fine operation in the integers. So although I don't have a GLNZ, I have an SLNZ. And that's weird. That's kind of weird. Weirdness. But it's a group. And sometimes I have to play with them. How are we doing so far? That was just 14 of poor Sean and Kyle's group. We have 15 and 16. Let's see how we're doing. Yay, I got a thumbs up. We're not all bad. Yay. 15, more complex numbers. 1, -1, I, -I under multiplication, where I is the I, square root of -1.
We, at first we thought no, because we didn't think there'd be inverses for the eyes, but then we realized that multiply eyes and negative I, we get 1, so we said yes.
Yes, exactly right. Exactly right. This one is a group. It's got closure. You can try, and the way, when you have a finite group, when this is coming up, when you only have a group with 4 things in it, or is it a group and you have 4 things in it, you could just kind of try all things, right? It's not so big. So you could say, I tried multiplying every pair of things together from in there, and I kept getting a thing in there. Multiplication is associative, so we're all good. 1 is typically your multiplicative identity, and 1 is in this set, so you're good. And then you just have to check for inverses. And 1 will be its own inverse, -1 will be its own inverse. And so Kyle and Sean said, like, well, we weren't sure at first. And then we realized that if you multiply I times -I, you get 1. So these two things are each other's inverse, and the other things are their own inverses. And so you're good. You've got inverses. And you could make a little Cayley table if you want to check how it all works out. Right? So this one is a group. And I don't think there's much more to say in our little document than yes. There is a more general group here. Sometimes I have people do exercises with it if they're comfortable with complex numbers, and sometimes I don't. I will mention it, but probably not do it because I think you all seem like you're a little less comfortable with complex numbers. And like I said, look how many examples of groups we have. We can stay away from the complex numbers if we need to. We've got lots of other examples. In general, 1, -1, I, that's not where I want to be. There we go. In general, 1, -1, I, and -I are what are called 4th roots of unity. There are 4 of them, and they're all solutions to the equation x to the 4th is equal to 1. You can have x to the n is equal to 1, and the fundamental theorem of algebra, which is another super important one because it's the fundamental theorem of, right? It tells you that tells you that if you have a polynomial of degree n, that has n roots, counting multiplicities. So in general, if I'm looking at solutions to the equation x to the n is equal to 1, there should be n solutions to that. And the n solutions to that are called the nth roots of unity. And they form a group under multiplication. But that's not a thing that we need to get into if we don't want to. It is something that he does examples of in Gallian, if you're curious, with non-4th roots of unity. So anyway, cool. All right, how about 16? What do you think, Kyle and Sean?
We said yeah, yes for that one too.
Yes for that one too. And so what did you do to convince yourself of that? We don't need to go over everything in great detail because we want to get out on time, but what did you think?
That it would be closed because if you have like integers, you're still going to get integer in the eyes.
Yeah.
The identity is 0 and the inverse is just the negative of the A and B.
Mm-hmm. It's very similar to the integers, in fact. You're just treating everything component-wise, and like you said it so well, Sean, like the I is just sort of sitting there. It's just sort of sitting there. If I changed it to like an X, and we were thinking more like polynomials, like it really is just a placeholder, the I. So this is a group. This is a group with a special name. This is sometimes called the Gaussian integers. It's integer-like, and Gauss studied them. So the Gaussian integers. Let me write that so you know how to spell Gaussian. So yes, these are the Gaussian integers. You might actually find people who say that S differently than me. I'm not sure I say it correctly. Gaussian? Gaussian? I'm not sure if it's a S sound or a S sound. Gaussian or Gaussian? You can't tell with my mask on. It makes no difference. I would say he's German, yeah. So how is it?
I have no idea.
I was like, at one point in time when I was talking about Zahlen, I was talking about how we use so many German words in group theory, I had a student in the room who was taking German, and I kept saying things like, oh, I heard that this was supposed to mean like unique, and he's like, it means lonely. Like he had like all the corrections for me. So I thought I was doing this again where someone's like, oh, if it's German, it's pronounced as blah because I know German. That's helpful for me because I don't know German. Okay, these are the Gaussian integers. Go away, you. I don't want you. Okay. And they are denoted in a weird way. I put this on your little snap the other day. How do I make the Z's and the N's and the B's and the R's and the Q's with like that double line through it in tech? The command for that is mathbb. I can't remember. B is maybe like bold block or something. It stands for something along those lines. Mathbb is Z adjoined I. Said Z adjoined I. Yeah. And that will look right notationally. Scroll up a little bit. Yeah, there we go. So if you want to denote this set, you do the Z for the integers, because this has something to do with the integers, square brackets, and then the I in there. That square brackets is read adjoin. The word for that is adjoin. Z adjoin I. Cool. I don't do a lot there, but I do some there. In that set, because it's kind of cool. Ah. All right, we've almost made it to the end. This is very exciting. So let's see. Now we move on to Lexi and Ben and Liz's group, and I've got all of you here, 2 of you in the room and 1 online. Who wants to be the speaker for 17 through 20? Liz, were you speaking up?
I just said hi, so I'm here.
Oh, you said hi from here. Hello. Okay. So Lexi's got the Kaylee table for this written out on her board right here. If you don't have it, Zoomers, that's okay. I showed you in the snap how to make Kaylee tables for U groups in Excel in under a minute. So we can do that super fast now. Awesome. So tell us about it.
So 17 said yes because what was it? And we know it's associative. This was the Kaylee table, I believe, was meant to show us the
Yep, the Kaylee table will show you inverses.
and then the identity is one like the other multiplication.
Mhm.
I don't know how we got that part, but
Your Kaylee table will show that, right? Because your Kaylee table models for you every possible pair of elements being combined. And so if the only entries in your Kaylee table are entries in your set, then you've shown closure. A Kaylee table will show you everything except associativity. That's harder. But since I told you associativity is free, making a Kaylee table for something and saying, look, there's a 1 in every row and column, that means everything has an inverse. Everything inside my Kaylee table is part of my original set. And having having a row that takes input and just produces like kind of the header for that row shows your identity. So everything about the group except for associativity appears in a Kaylee table. Another reason that people thought Kaylee was crazy and that associativity was really annoying, right? because Kaylee was like, look, all the things you could see in my Kaylee table, except associativity, that one's weird and you can't see it here. Shh. Weirdness.
Our homework groups, are we allowed to just say, we know it's associated because you said that.
That's exactly what you should do. So in your homeworks, when you have a group or you have a thing and I say, is it a group or not? The exact thing you should do is say, this operation is associative. You should just assert it, even though you haven't checked it. You should just say, this operation is associative. Then what you're communicating to me is that you know that associativity is part of the definition. You didn't just leave it out, right? You've communicated to me that you know that it's part of the definition, but you don't check it because you don't want to do it and I don't want to read it. Right? That's the perfect compromise for me. Yes, these are the U groups, and we worked out a Kaylee table, and that was helpful for verifying everything for us. So that's 17. And then we get to this wonderful string of 18, 19, 20 where things are really similar. And so we know we can like get through them all like relatively quickly because that's the thing we've been doing. So what do you think, Benjamin? You think 18 is a group, the set of polynomials with real coefficients under addition? You said yes, it is a group, and you're absolutely correct. What does your, if I add two polynomials, get a polynomial. Associativity is cool because it always is. What's your identity look like? Just 0. 0 is a polynomial. It's constant polynomial, but it's a polynomial. So it's 0 like it always has been. How about inverses? What do inverses look like? Absolutely right. Oh my gosh, I just started coding in Python. That's not what you're doing, Sarah. No. When people talk, you use quotation marks. In Python, you use single quotes. And so I was like, single quotes, that's what you say, right? Yeah. Colin, what's up?
So instead of polynomials, it's like ax plus bx squared. Like you're just adding right?
Yes, my set of polynomials would look like constant plus some other constant times x plus some other constant times x squared plus some other constant times x cubed, and I would let your degree get like arbitrarily large. Yep, that is my set of polynomials, and that is a group. And I would say this allowed like S adjoined X. So the square brackets are always read as adjoined. It's kind of like you just like joined on this other thing to a set that was working, and it's really the set that's doing all the work. As you were indicating, right? Like it's 0 that does the work of being the identity. Associativity works because everything's associative. Let's get answers to the last two and then let's clean and get out of here. I know we normally try to pack up early, so I just want to answer yes or no for these. 19 yes and 20 no. Those are correct. And I'll leave the course log as it is because somebody can go and type those things in and like maybe say why, and then that's community points. So perfect.
Oh, yeah. Okay, I get credit for that.
All right. We're all good for today. Zoomers, thanks for joining in, and I will see you soon.
Thank you.
Have a good one.
Bye, thanks.
Thank you.